Hello, folks. I'm here to talk to you about making Linux kernel builds and kind of a little bit of the life of a distro Linux kernel maintainer. My name is Neal Gompa. I kind of nowadays call myself an open source advocate. You might have seen in previous times and eons gone by. I would also call myself a professional technologist. I left it off mostly because I didn't want the bullets to get too tiny. If any of you were at the previous talk that I did with Davida Kavalka about Fedora Asahi Remix, you know, he kind of joked that every time I do a presentation, another bullet point grows on this list. I am trying. But I am the owner and principal of Velocity Limitless, which is a place that, you know, does engineering around this kind of open source stuff. And, you know, as part of doing Velocity Limitless stuff, I'm a contributor to Fedora, CentOS, OpenSUSE, and Magia. And through those, I have a litany of roles within all of these projects that I'm not going to read off to you, but you can feel free to look at it and gaze into all the things that I have done there. I contributed to a lot into the base system stack, notably with package management and system software delivery with RPM, DNF, Kiwi, Koji, OBS, similar things. I'm also a KDE contributor. I'm a member of KDEV and most recently of the Xorg Foundation. Yay! And another thing that is I'm a co-host of the Pseudo Show podcast. Check it out, it's fun. Well, there'll be hopefully some new episodes coming out real soon where we talk about the business of open source and the intersection of all the things related to open source in wide commercial and personal use. So we're actually here to talk about the Linux kernel, not about me. So we'll talk about the Linux kernel. The Linux kernel is special and maybe also is not special. Kind of depends on how you look at it. So when you look at how the Linux kernel is simple, maybe it isn't so special. It's written primarily in C in assembly, has no external runtime dependencies, which you could arguably make it special, but you know, in different ways it's not special. All the subsystems and drivers are included in the kernel, and it is substantially well documented. Although if you compare that to the variety of open source projects that are out there, being substantially well documented is special in a good way. But it's also complex, you know, so they've just added Rust to the next set of languages that are in the mix. For better or worse, depending on how you look at it. But it does add some complexity to the stack. It builds user space components that are tightly coupled into the kernel with the kernel that's built. So for example, you have things like libbpf and perf and things like that that are actually not for kernel space but for user space, but they have to be tightly matched to the kernel to be actually useful. Now, in recent years, there's been this tug of war between whether they want it to be tightly coupled or not. We've seen this go back and forth. I think now we're at the tug of war where they're now tightly coupled again. Probably in a couple of years, we'll see them pull back to be a little bit more lax. I just assume they're tightly coupled now because that's just easier for your own sanity, and I recommend all of you do the same. All subsystems and drivers are included in the kernel. Notice I listed this in both categories, and the reason for that is very simple. Because it's all in the kernel, you have to actually, to some degree, understand every subsystem and every driver as part of maintaining it and supporting it. That means that you're looking at, when having to deal with a concern around a particular driver, you have to dig into it, and you have to kind of understand what the domain of that driver is, what it's trying to do, and how you're going to deal with the problem related to it. Whereas if you look at other operating system environments where the drivers are decoupled from the main kernel code, that's not your problem. And all of it's your problem. And so that's, from that perspective, I consider it complex. The build tooling is sufficiently complicated to necessitate its own bespoke program. So this is fun. When you look at how the Linux kernel is actually built by itself, in theory, it's simple. It's just a bunch of makefiles. No. In practice, it is a bunch of makefiles that can also call back into themselves. It's recursive make. It has a bunch of other fun stuff like that. It has variables that go upwards and downwards and sideways. And the documentation about what those variables do and what they affect and how they do things to the kernel build is weak. And so because it's so complex, there's a lot of scaffolding and extra tooling, either within the Linux kernel code base to work with it, or sometimes distributions do their own tooling on top, and we'll talk about that in a little bit. But you tend to see specialness all over the place because the Linux kernel build system, which is, I believe, formally called K-build, is completely within its own realm. It's not in the realm of crazy like something like, say, Bazel, but it is up there in the realm of, I don't know if I am happy that I have knowledge of how this works. So when you're building the Linux kernel for yourself, there are a few reasonable choices and a whole lot of unreasonable ones. So I'm going to cover the reasonable choices, and I'll talk about why they're reasonable. So you can seed the build from your running kernel using make local mod config, or its variant if you want everything built in and you want an 800 megabyte kernel image, local yes config. Don't recommend that. As it turns out, side note, all yes config, mod yes config, local yes config produces images that are so big that it can't be loaded by any bootloader, and it can't be loaded by firmware. So don't. Seeding a build from an existing kernel, old def config. So if you've done a kernel build before, maybe you're upgrading to a new kernel, old def config is useful because you have maybe the config that you used the last time, you put it in there and you run make old def config, and any gaps that have been discovered as part of trying to run the build again, it will fill in default values, and hopefully you get a usable kernel. Making the kernel with all the things, as I said, all mod config. This is, well, what it says on the tin. It'll turn everything on, but if anything that can be turned into a module will be built as a module, and everything else will be turned on as yes. These very simple 3 modes are probably where the vast majority of people who want to experiment with building the kernel are probably going to start from. And these are all reasonably good choices because no one has any clue what all the things do. There are hundreds of knobs in the build for the kernel, and not all of them are really all that well described, and you're not necessarily going to know what the consequences of them are. So it's a really good idea to kind of think about taking something that you know that works, working from it, and then tweaking it over, to try to get a better understanding of things. And then I list the slightly less reasonable choice of doing it interactively and selecting everything individually. So there's a number of different ways to do this. Make-X config gives you this nice, pretty Qt-based front-end UI that gives you little help thingies and descriptions if they're filled out in the metadata. Or you could do make menu config, which gives you an ncurses type UI. Or you could, apparently, there's a GTK version of this that's not by default, and I don't know why it's there, but sure, make gconfig, and that'll give you a GTK UI for no reason at all, but it's there. But the idea is that you can go through this individually, and you can look at them and make choices. This is great, I think, if you're trying to build really small kernels, if you're trying to build something for an embedded platform where it's super easy to decide what things to turn on. And the reason why it's that way is that oftentimes there's a super switch of some kind that you could say platform foo, like platform Raspberry Pi, and that just turns on all the right drivers and all the right things for that and turns off everything else for you. But if you are outside of that and maybe dealing with more generic things like x86 PCs, this is going to be an adventure. Because as it turns out, computers are complicated and there's a lot of stuff in there that you don't know about. So I wouldn't recommend it, but if you are one of those, want all control over all the things, it's a great way to kind of learn where all the things actually are. And maybe if you want to do it in a VM, which actually I recommend, doing make xconfig for building a kernel for a VM environment, it's a well-defined platform. There's actually documentation about what your hypervisor actually provides as hardware. It's a great way to kind of learn how all the pieces lock in together if you want to get a better understanding of how the kernel piece goes together. Oftentimes I do stuff like that where I use make xconfig to just say platform VMware, and then I have my VMware hypervisor knobs, and then I can use things like old def config or local yes config to kind of see how the different permutations of things work. And that's really useful and helpful to try to understand what the impacts are of choosing the different modes. So for example, the difference between having things as modules versus having things all built in. Or if you're one of those people who's like, I don't want to have an init RD or an init RAMFS or whatever you want to call the first stage boot, if you want to get rid of an early boot stage, while in theory you don't need to get rid of kernel modules, in practice you do if they actually involve early boot, like setting up disk controllers or graphics, because nothing will show up, and then you can't mount your file systems, and that's not great. But, you know, those are all the kinds of fun experiments you can do as an individual for that. But keep in mind, building a kernel for yourself is still a lot of work. This is a cross-section of a subset of a kernel that exists that I've used on one of the environments that I have built out. And you can see that it's a lot of knobs, and while I know what most of them are, at least a couple of them I don't know. Like, obviously config bug on data corruption sounds real bad, and I would really like that, but I actually don't know what that does. And then config BT, I mean, I think that means Bluetooth, and some of the other things make me think that's Bluetooth, but it could be BitTorrent, I guess. I mean, it's not, but those are the kinds of things. Like, a lot of these are very terse names, and there are no descriptions in the config files that you use for the inputs of things like make old def config and whatever. So you kind of need to be able to have lookup powers by being able to read and sort through the make files and understand where they're coming from. And it's really helpful to do a couple of times doing it interactively to kind of see what the hierarchy is. And then you can understand from mapping that to these config files. But again, it's still a lot of work to do this. And again, we're not even talking about changing anything. We're just talking about building. And again, it's a simple case that we're talking about right now of building it once. When you scale this out and do this over time with lots of other things, you will find yourself doing the process sometimes completely from scratch, because a bunch of things have changed and there's no reasonable way to infer from what you previously had before to what you need to have again. A couple of times one thing I saw was in one kernel upgrade, I think it was like a few years ago, I went from a kernel that had an option for a driver that was one name, and then the next release it changed to another name. But if you did old def config, the old name went away, and the new one doesn't have any reference to the old one, but the new one has a default of no, so you just suddenly don't have it. And you don't know that you don't have it because you don't know what you're missing until you try it, and then you suddenly realize, hey, why isn't my keyboard working? Oh, it's because the USB controller driver got renamed for some reason, and the default for it is no and not yes. So that kind of thing can happen, and that's annoying. And this is the crux of, like, even if you're just doing simple, like we're going to build and keep upgrading and then build again, is difficult because the kernel doesn't have stability for anything inside of the kernel. And that even includes the build tooling. The build tooling is intentionally not stable. They don't provide a contract for how that works other than the make commands will do as they are written out on the text literally. So old def config will do exactly what it says, but that doesn't mean it'll do what you want it to do. So those are the kinds of things that can happen. And yes, and the kernel can also, the kernel build is also capable of attempting to wrap everything up into a package and install it properly. There's, make bin RPM package or build deb or snap or whatever. Yeah, and it doesn't work because a lot of times those things don't necessarily match the distribution that it's being targeted for. So yes, it's fine to try it and see what happens, but if it turns out that it doesn't actually integrate with your system, you're going to probably want to take a look at what's going on in that packaging and adjust it accordingly. I know that I think in the last 2 or 3 kernel releases, the Asahi Linux people actually made fixes to the RPM spec file included in the kernel tree, because doing development without being able to turn it into a package and install it and being able to roll back and forth is super painful. And so having a simple spec file and having a simple way to produce a package that you can install is very valuable. The Debian package, I think, got revised a few releases ago, like last year, 2 years ago or something like that. But a lot of the packaging that's inside of the kernel source tree is not exactly in the most shiniest of states. But it's also an easy place to contribute if you want to, if you find something's not working and you can make a fix, they'll take it. It's always useful to have those working, but it doesn't mean that it's going to work just out of the box, is basically what I'm trying to get at. So the Linux kernel for distributions has to take a little bit of a different tack because they have to care about a fair number of things on top of the stuff that you have to care about if you're just doing it for yourself. You know, one of the bigger things that, you know, I alluded to when I said that, hey, when you upgrade these kernels that you wind up having a problem knowing whether your drivers are all enabled when they're supposed to be, is tracking build options based on features, architectures, and distribution needs. Almost every distribution has some kind of script that actually inspects all of the makefile trees and all the config states to check for deltas and changes to be able to detect things like config option renames, dropouts, adds, things like that, and to try to be able to create some kind of inference of what new switch mode needs to be done. This stuff is not very good, but it is a starting point, and it at least makes people aware that something has changed. In a lot of respects, that's pretty much enough to make sure people find out and fix it. Another aspect is executing kernel builds in an isolated and reproducible way, and that's actually like kind of a cornerstone of Linux distributions. Like most software, nobody assumes in the build scripts that you're doing it clean. And in fact, a lot of the commands inside the Linux kernel build scripts, some of the commands actually depend on a quote-unquote unclean system. For example, all the local foo config modes depend on pulling the config from your running system to be able to create a new kernel build. And that is very useful if you're trying to test patches or whatever, but it is very annoying if you actually want it to do an independent build based on an independent config that doesn't have a relation to what you're running on your system. So a lot of times, I mean, it's not that there aren't modes that do absolutely do this, like the def config modes and things like that, but generating the configs and then making sure that they are actually used is extra stuff that a distribution does to make sure that their tooling does the right thing, because otherwise you get weird surprises. And like, hey, a flag you set because it was there and now it's not, but it doesn't throw errors when you pass an option that doesn't exist, because all it is a make variable. So, hooray? Stuff like that is actually something that they check. But and of course, the integrating with the distribution machinery. I mentioned this earlier. The upstream spec files or Debian packages or snaps or whatever don't necessarily integrate with the distribution machinery. Whether you have grub, whether you're using some kind of hooks with systemd, or you're using an init ramfs like Drakit or whatever, like those pieces all have to be plugged in somehow. And unfortunately, we don't actually have a standardized path for handling this stuff, so we can't just have it in the upstream kernel code. Every distribution's got to do it a little special. And the last bit is something that you don't really see a lot in community distributions, but you see it more in the enterprise Linux distributions like RHEL and SLES. You see backporting features and fixes to align with the user space needs and the requirements, because, again, remember what I said about how the kernel includes user space components and things like that that are kind of tightly locked with what you have in the kernel itself. At least in enterprise Linux distributions like RHEL and SLE, RHEL being Red Hat Enterprise Linux, SLE being SUSE Linux Enterprise. Those two, what they typically do is they break out the user space components and they build them as separate packages. And those get updated against the will of the kernel. So they get updated out of sync, and that means that the kernel needs to have things backported to make that user space component work as expected. So things like that can happen. And then there's, of course, other pure user space things that actually technically require, you know, syscall interfaces or things like that that exist in the kernel that maybe came from a newer one but need to be brought back because XYZ application uses ABC feature, which, oh well, you have to deal with it. But these result in distributions implementing tooling on top of the Linux kernel build process to enhance it for these needs. So in particular with Red Hat distributions, all the kernel stuff goes into a central repository called the Always Ready Kernel, part of the Continuous Kernel Integration Project, otherwise known as CKI. Yes, I didn't choose the names. Don't look at me. I don't know. They could have better names, but this is what it is. I live with it, so do you. But this Always Ready kernel stuff that is mostly around the idea that at any point in time, the tree can be branched or forked to create a RHEL kernel that actually works, because it continuously tests both the RHEL and Fedora configs inside of there, or in theory, any other distribution variant config. And this is necessary because, particularly with Red Hat Enterprise Linux, they fork the kernel at a particular point in time, freeze the version, freeze the interfaces, and then backport the hell out of things from the future back into it. And that is, there are many talks and papers about how that process is done. I'm not going to get into it, but it is an important factor to consider about the design choices of this, because if they didn't do it this way, you're talking about a kernel package SRPM that has probably somewhere close to 500,000 patches by the end of a RHEL life cycle. That is a lot, and I promise you no build system can handle that. Well, maybe not 500,000, but a lot. It is many tens of thousands and maybe hundreds of thousands. I think at one point I saw one that was like 89,000 patches when it was all blown out based from the tag that it was branched from and pulled all the way up. And it's like, oh, yeah, I see why you don't maintain these as patch files on top. That's a lot. And in Arc, the way that it works is there's a Red Hat folder that's mangled into the source tree or merged into the source tree that includes all the distribution setup scripts, and then it's hooked back into the parent make file. So they modify the parent make file at the top of the tree to call into the Red Hat folder to do all the things. A notable feature of this particular setup is that all the configs that you set, if you remember from a few slides back, I showed you this list of config options that are being set. In the Arc setup, each config is actually a small file, and what it does is it goes through and evaluates each of the config options and generates the kernel build system compatible config file after verifying that all the options exist. And because it does it that way with a per file option file thing, it is very easy to track these things from commit to commit to understand what's been changing and what's going on. So coming down from Arc into talking about the Fedora Asahi remix. So the Fedora Asahi remix is a derivative of Fedora Linux optimized for Apple Silicon. As I gave the talk yesterday with Davida Kavalka about the Fedora Asahi remix, there's a lot that goes on in there. This is just purely the kernel part of this. In the kernel part, it comprises of 3 major changes: a large patch set from the Asahi Linux repo targeting a major kernel version, so for example 6.6. The configuration changes to turn it on, so everything is pretty additive. It's designed to be additive so that you can just switch the knobs on and get that done. And then enabling a 16K page size flavor for ARM64. This ARC model helps by allowing us to reliably maintain it in a way that it minimizes split brain. So for those who don't know what split brain is, it's the concept of which something lands and then something is changed at different intervals, and they don't line up, and so something breaks because they're not coordinated correctly, and so you get weird states in the end. This is one of the reasons why, if you look at CI/CD stuff, nowadays your CI definitions are inside your code repo, because when you make code changes, you want to change the CI at the same time. In the era before this, where the CI stuff was in a separate repo or stored in the application or somewhere else, somebody would change the code. But the CI wasn't changed to go with it, and so all the tests fail, and then it can't land because the tests haven't changed, and no one likes that. And this is the same kind of approach. If you're changing config and you're changing modes and you want to have all that all tested, you want it all to happen at the same time, that's one of the advantages of this particular approach. But the challenges in building this do not start at the beginning. They come from moving to newer kernel versions. So getting actually started and getting a kernel out the first time, it's easy. It's you bring it up, you pull the patches in, and you turn on the features and you're done, right? Well, the next time you have to do this, then you got to pull all those changes up, and you got to reapply them on the new version. You have to make sure that they work, that the code changes underneath it haven't broken something, and they inevitably do, because the Linux kernel maintains no stability in its own code. There's a document inside of the kernel source tree that explains that you don't actually want this, because the trade-off for this is when you have that kind of stability, you can't really do major architectural fixes very quickly, because you have this, backwards compatibility and forwards compatibility concerns, and they just don't have any of those. And this is a very common thing to happen, and this is one of the reasons why, if you look at Linux distributions that operate in a way that they engage with the community, they tend to say, we want you to have these changes upstream. We will only backport things that are in the mainline tree, because ultimately they don't want to carry it forever. And with Fedora Asahi Remix, I have to carry the patches basically forever until they land. And it's been 2 years now, and the patch stack hasn't actually gotten smaller. And one of the consequences of this that kind of sucks is I can't actually move to new kernels as quickly as Fedora does. Fedora's mainline kernel basically has almost no patches on it. Actually, at this point, I think it's at no patches because we got rid of the last of those when we got the secure boot lockdown feature merged in like 2017, 2018 or something like that. And so the Fedora kernel typically doesn't have any patches other than maybe select backports when the bug has been discovered. That's already queued for stable and will go away eventually. But for Fedora Asahi Remix, we don't get to benefit from that, and so what ends up happening is that sometimes it takes so long that we wind up skipping kernel versions because it took so long to actually get things working again. So to give this a concrete example, Fedora Asahi Remix is currently on the 6.6 kernel series. It has taken so long that we are skipping 6.7 and going straight to 6.8 because, well, 6 weeks have passed since the last time we did it, and a new kernel has come out. Well, 8 weeks, actually. I think that one had an RC8. But point being, a month and a half has passed, new kernel. Everything we did is just now pointless. So we got to go do it again. In reality, we didn't actually spend enough time for this to be a waste. But there have been cases where we've actually gotten just to it at the time that the new kernel's coming out. And now we have to start the treadmill all over again. And we have to decide whether or not it was worth actually releasing that version or not. And sometimes the answer is no, it's not worth it. Because it also takes time to test because you have a lot of code that is somewhat peer-reviewed, somewhat not. Most of it is peer-reviewed because the Asahi Linux project actually requires peer review for even patches landing downstream. But it's not integrated in the upstream stuff, so when the upstream stuff changes, then that means all the patches have to be rewritten, and it's a whole new test cycle, and it's a whole lot of extra work. Sometimes we observe very strange things like Wi-Fi suddenly not working, or Bluetooth crashing when trying to use it, or reboots. The reboot signal not actually being respected from because something just changed about how the watchdog is working, or how the mailbox, the mailbox subsystem that actually handles power signals is done, or whatever. Like, there's a lot of those things. Or the UA API changes for graphics, and suddenly none of the drivers work again. And so that has to be fixed. Stuff like that happens. So that's kind of Fedora Asahi. Now we go to CentOS Hyperscale, which is the other kernel I maintain. So CentOS Hyperscale is built on CentOS Stream, the immediate upstream for Red Hat Enterprise Linux. This means the default for CentOS Stream is actually the RHEL kernel, or the kernel that is for RHEL. It calls itself the CentOS Stream 9 kernel. Whatever phrase, pick what you want. But the RHEL kernel is derived from a specific Linux kernel version, and features and fixes are backported in such a way that the behavioral and API stability is somewhat preserved. So they try very hard to successfully lie about what kernel version they are. So if you look inside of the RHEL 9 kernel as of, I think we're on, what, 9.3? If you look inside the source tree, it still says it's 5.14. But if you look inside, for example, FS, XFS, you're going to be weirdly surprised that it looks like 6.3. So you get to be surprised that it's like some of these things are so far up, some of these are kind of behind, some of them are in the middle, and a lot of them are broken. And that's just kind of the consequence of this particular style of maintenance. Building a variant with different features became very difficult. Initially, the CentOS Hyperscale spin used the RHEL kernel with different config mods and tiny changes that we backported or contributed to the RHEL kernel. Over time, it became more difficult to do that, to the point that I couldn't release kernel builds anymore that worked. And so I got kind of personally fed up about it and switched over to building from the Fedora kernel. So CentOS Hyperscale is still built on CentOS Stream, but that doesn't mean that we have to use the rel kernel, so we don't anymore. And so this is now branched directly from the Arc repository, just like the Fedora kernel is. And now we go down to just doing config knobs. And with no significant patches and no non-merged patches, I can make new releases really quickly. It is very easy for me to pull them off, and it's really just a function of, can I spend like I think it's like 2 hours of doing the build and test before uploading it and having the build system do it, which takes another 2 hours. So it's basically half a day for doing a kernel release. And yeah, once that's done, we move on with our lives, and I can do other things around this. But the nice thing about this, moving to this process, is that I can just get them out the door. And because I'm mostly just doing config changes and any other non-config changes, I can contribute to either upstream Arc or further upstream the Linux kernel, depending on what is appropriate. I am not maintaining long-term deltas, and I don't hit the downsides that occur right now with the Fedora Asahi remix kernel, where I really have to work very hard to make sure that things are actually working before I can release it, because it probably isn't out of the gate. Sometimes I'm lucky. It works just straight away. Those are good days. But so what about other Linux distributions? We talked about CentOS and Fedora, Asahi. Other distributions have their own approaches to this. So the SUSE distributions use a repository that's confusingly called kernel source. And that is actually not the source code of the kernel. That is the source code of the patches and scripts used to generate the packaging files to then build the kernel in the build system. So this they as part of their setup, they export another repository called kernel that actually includes a fully constructed Git tree of all the things. The kernel source export goes to the build service, the OpenSUSE build service, and the prepared source tree just goes to another repo on GitHub so people can look at it. Debian uses a packaging repository that contains a makefile that dynamically constructs the build flags and options based on the vendor, target architecture, and kernel image variants. To build that package, the sources have to be separately downloaded, and the source trees have to be merged before running the build. So Debian does what in some circles they call split packaging, whereas Red Hat and Ubuntu do what's known as merge source or source Git packaging. Source Git is a confusing term, so merge source is much easier and explains what it is. Ubuntu uses a variant of the Debian style, but they merge the sources with it for the similar reason that Arc does. So Ubuntu basically takes Debian's kernel packaging as its upstream, pulls it down into its own kernel source tree, and then starts cherry-picking, backporting, or adding custom features into their kernel. They call this, if you look in their Git history, they call it Ubuntu sauce. And you can always find them if you type in the words Ubuntu sauce into a Git log search. And you'll get to see all the sauce that they add. Each Ubuntu version has its own repository named after its code name. For example, the upcoming Ubuntu 24.04 LTS has the Noble repository because it is a noble something or other. Arch, Magia, and OpenMandriva all have simpler packaging schemes that are much more similar to how you would do it as an individual. It's a unified, simple config file that is just updated alongside it. It gets, injected into the makefile build system, and it gets picked up and it gets run. So this is the closest to how an individual would do it. And it's actually pretty similar to how the packaging works with for example, the spec file that is included inside the Linux kernel tree if you were to actually run it instead of doing it from the makefile. So when you're talking about this, the point I want to make is that building the Linux kernel for distributions is really about the long haul. You want to be thinking about how you are going to keep up with it over the long period of time. So that means a lot of times you see packages, and this is not just the Linux kernel, this is pretty much everything. If you look at any Linux distribution, the packaging is optimized around, okay, you have a lot of upfront effort, and then for the longer term, you have this payoff of not actually having to do a lot of work to keep things up. If you wind up being in a situation where you have to do a lot of work every time, then something has gone horribly wrong, because The idea is that it's not supposed to work that way. So, but in spite of the differences, as I outlined with, Fedora, Asahi, CentOS, Hyperscale, even SUSE and Red Hat and all these other, and Ubuntu and Debian and all these different ways that they do the packaging, these characteristics are all there, right? This idea of being able to trace the changes, of being able to verify things before running a very expensive kernel build to make sure that the options are all set. Everybody has these scripts, these little apparatuses that they build around it to make sure that they're able to build it properly. And all of them don't have documentation for this. So that's a common thread as well. So just like any other open source project or most open source projects, what the distro does to actually build their kernel is often not actually documented, and you kind of just have to poke at it and figure it out. But these maintenance strategies are all optimized around what they're trying to do. So you see Ubuntu and Arc optimized around the fact that their kernels are going to collect a lot of backports and non-upstream changes over time, and so they have full forks of the repos, and Debian and Arch and Magia and OpenMandriva, they don't do any of that. They mostly take the upstream, maybe have a few patches here and there, and the lifetimes are short enough that it's not a big deal, and so they don't fork the Git repos because there's no point. Well, there's no need. There might be a point. Who knows? So that's it for like my prepared bits of this. Questions from anyone? Okay. Well, okay. Let's see if I can. Here you go. I am not eating anything.
Have you...
Is it working?
Cool. Have you contributed to the upstream K-build project? It seems like if the RPM build isn't working, there might be an opportunity there to make things better.
I've thought about it. I've thought about contributing to, so the question was asked, because I'm not actually sure if the microphone is actually working. The question was asked that, have I thought about contributing to the upstream K-build project? And the answer to that, because that's what, the K-build project is actually what owns the build mechanisms for all this stuff, whether it's building an RPM or building a deb or a snap or whatever. I have. I don't use that mechanism enough myself to really have to deal with it. But I would, if I'd hit a problem and I knew how to fix it, I probably would send a patch anyway. I mean, I think I have a grand total of maybe one patch with my name on it in the Linux kernel, and I have a few, maybe like 5 or 10 patches, which have my name listed as either co-author or reported by or some other fancy tag or act by. Well, I have lots more that are act by and reviewed by, because I've been doing reviewing of kernel patches a lot lately because of the Asahi stuff. Everyone says they want more reviewers, so I try. We'll see how that goes. So yeah, I mean, I'm not closed to the idea. I certainly could. It's just I haven't had a reason to myself. Any other questions? Yeah. Try tapping it to see if it actually works. Yep, that works.
Which distributions do you think have the best developer experience for a local developer wanting a quick build test cycle?
Good question. I would probably say that the one that has the best workflow, it's a toss-up. So Arc has a good workflow if you are primarily cherry-picking fixes, committing new code on top, and then being able to just hit the go button to run it, and you didn't need to do any config knobs or whatever. The config knobs are actually the real messy part, because in Arc, the structure for the config knobs is that they're actually divided up by targets. So you have common, which is the base one that applies to all distributions that are used in there. Then you have a rel folder, that's for the rel target, and then you have a Fedora folder for the Fedora targets. And then there's the secret override folder, which applies to all targets. And no one knows that the override folder exists. But if you create the override folder and put a thing in there, then it works on all targets, and you can test to see how it works across the different combinations. The fact that that is quote unquote secret is actually the biggest problem I have with it. It's not that it's secret, it's that it's just, again, not documented. And because they keep changing how this works, it has, like, as some of the other members in the Hyperscale SIG are aware, like, during the time frame that I've been maintaining the Hyperscale kernel, I basically had to rewrite my own scripts for maintaining the kernel multiple times because they kept changing all the commands and all the flags and the methods and invoking them. So if they decided to stabilize and like not change it every like few months, it would probably be an okay experience, because then at least at that point somebody could write it down and it would actually work as it said on the doc. If taking Arc out of the picture, the other one that's kind of, I think, an okay experience for it is, I would say, the OpenMandriva build, because the OpenMandriva stuff is interesting in that they've hacked their RPM to be able to do cross-architecture builds. So they have a way to cross-compile any and all packages on it, through it, with automatically handling, triggering emulation for the check section while not doing it for everything else, and other fun stuff like that. Because Bernard Rosenkranzer, who is the lead of OpenMandriva, mostly works on embedded platforms, and he used to work for Linaro for a really long time. So there's a lot of that kind of influence in the way that OpenMandriva actually works. So, and the spec file is easier to understand. That helps too. So when you're working from just like maybe just applying a patch or two and just appending it into the spec file and then setting a knob by appending it to their config, that's really easy to do. But otherwise, and so I would consider it a toss-up. It's based on what you actually want to do. But like the SUSE one and the Debian ones really suck, because the SUSE one is a bunch of YOLO scripts that you kind of have to run in a specific order, and it doesn't tell you what the order is, and so you can get some very interesting results. The Debian one sucks because it is actually really, really hard to understand how the Perl make generates the config file. There's a double Debian folder, so they have a Debian and a Debian.master, which then calls into itself, that generates the files and puts it back in and rewrites the build as it's running so that it re-executes itself and does things. That's terrifying to reason and scares the crap out of me. I don't like it. Yeah, so that's kind of how, and Arch is, of course, dead simple. They just put the bloody config file in and just run it. So it's, but like adding patch files and making sure that they actually work, and then tracking what the build does, and being able to do it in a way that's isolated, reproducible, is a pain in the butt on Arch. So I give it points down for that, because you'd get unexpected side effects from your host environment. Like make package by default doesn't give you a chroot. It just does it on your system. This is how all the AUR helpers work. This is how all that other stuff works. So you just get into no fun land when you're trying to figure out what's happening. So for a lot of packages, not just the Linux kernel, I consider kind of the Arch stuff to be kind of the bottom tier here for that. They traded away a lot of complexity, and in a consequence also traded away a lot of reliability, which I'm not a super big fan of.
Thanks.
Yeah.
I'd like to ask, like, what's diffconfig actually good for if none of the distributions are using it?
I'm sorry, what? I didn't quite get.
So, like, there's make diffconfig, right?
Yep.
Yeah, but, like, none of the distributions are actually using it.
Because the Linux kernel's not made for distributions, it's made for the developers. Right?
But
So
like
the whole make build process, all the things that are actually in there, they're not made for distributions. They're not made for users. They're made for the Linux kernel developers. This is also the reason why most of the apparatuses that Linux distros develop never make it into the kernel itself. Like, there's no technical reason that the config file needs to be one ginormous .config file rather than a bunch of... Is this like actually just being ashy? Let's just not. There's no technical reason why it can't be done in such a way that you could have each config setting be its own file and have drop-ins and stuff like that. Other than they don't care and don't want and don't need it. And they don't care to need it because for them, they're just maintaining this one big file and they just twiddle a knob and call it a day. Or they use the IK config, their in-kernel config, to source it and then rebuild their system with new code to see how it works. And for their workflows, it's not important. But for distro workflows where they're never doing host equals target, it matters a lot more. And so this stuff has to be managed differently.
Yeah, my question has to do with, and I definitely sympathize with the statement you had in your slides where like every change in the kernel needs to be easily tracked, testable, revertible, and moving towards minimizing the amount of effort needed. So being like somewhat newer to doing like kernel work, maintaining like different potential like kernel forks, I guess just based on like your presentation and in your experience, what would be like your suggestion for trying to maintain so many forks and different kernels? Like, is it the ARC? Like, I know you mentioned the ARC model a lot, so I just want to make sure I don't get it like twisted. Like, are you saying that's one potential good model to explore, or what would your advice be?
If you're largely code oriented around how you're doing stuff, the ARC model is great. Because the ARC model implies that you're a developer and that you are actually writing code into your tree, and then you want to build on it iteratively and test it and whatever. So the only reason the ARC model works is because it's tightly coupled with something called CKI, which I mentioned earlier. CKI is a project to do continuous kernel integration. What that means is that every commit, merge, change that happens, it runs through a battery of tests. It kicks off other tests, integration tests, functional tests, unit tests, the whole works, and tries to gate every change on those before they can land. In practice, we can't actually do that because the upstream Linux kernel doesn't do gating, and so there's no actual way to prevent bad code from landing. But what we can do is know when it's good or bad, and then be able to work backwards without having to use things like git bisect, which actually is hard to use when you have a code project that prefers to use merge commits that have nonlinear merging. And so nonlinear merging means that the histories are all wonky and bisect gets very difficult. And so being able to know when a merge lands, when you have the good and the bad state, means that you can narrow down things like your bisection and figure out what actually happened and things like that. They're useful tools in the tool chest that upstream Linux is not currently at a point where they all agree that they want. But when you have that, then what the ARC model has is very useful and powerful. When you don't have that, and if you're primarily relying on just building from the mainline tree and maybe having a branch with like maybe 10 or 20 or 30 patches, the ARC model might be a little bit overkill. But it also depends on your focus. If you're largely a developer type and not really used to the sysadmin type model of thinking about the process rather than the outcome, developers tend to think about the outcome, administrators tend to think about the process, and if you don't want to really think about the process, then the regular other models that other distributions do don't really fit. So that's really where it kind of lands down on. My personal preference, again, as someone who's done both sysop and developer stuff, is I actually would prefer both of these things to be split out. I actually would prefer that things that are packaging or distribution integration to be distinctly separate from the pure code parts, because you can't satisfy everyone with the integration of the two, and also you get a lot of unclean merges and things like that. This is mostly related to my opinion of how these things should be integrated. But from a developer point of view, the ARC model's great. From a sysop or an administrative point of view, you probably would like the SUSE version better, because it very cleanly separates how you're dealing with the individual pieces and putting it all together.
Thank you.
Any other questions? Okay, then. I guess that's it. Hey, and I even made it to time. Mostly.